Okay, this is worksheet 5. Number 2. Okay, I will solve this one 2 different ways, one with forces and torques and also one with energy. So we start with the situation where we have this going on. We have the pulley. I suppose my pulley doesn't look exactly right, so I'll change that. And okay, there we go. And that's what we have going on. All right, so if we label this one as mass 1, this one is mass 2, and I will call this one mass of the pulley. Okay. When we label the forces that we have going on with everything, we have a force, gravity of 1 here, and a normal. These are equal to each other. Then we have this force, which is the force tension at 1, and we have a smaller force backward that is the frictional force. The pulley has a force being exerted on it here that's tension 1 that's equal to the tension 1 on the block, and it has a force here that's tension 2. And we talked about it in class that tension 2 has to be bigger than tension 1, otherwise the pulley would not rotate. There's also gravitational force on the pulley and a normal force here keeping the pulley up, but those don't come into play with the rotation. And then on the bottom block, we have the tension force acting on it, and then we have the gravitational force. So those are all my forces, and now I have to do the sum of forces. So I'm going to call them 1, P, and 2 just to make sure we keep them separated. So 1 is mass 1. So mass 1, we're going to have sum of forces in the y direction. That is the normal minus the weight equals 0 because it's not moving. So I know that the normal equals the weight, and that's m1g. Mass 1 in this case was 5 kilograms. So weight 1 we're going to call 50 newtons. Mass 2 was 7 kilograms. So weight 2 is 70 newtons. And the mass of the pulley was 2 kilograms, with the radius of the pulley being 0.050 meters. Okay, we'll add other knowns as we need to. So the normal force is equal to 50 newtons. Okay, the other direction is the x direction, and that's the direction it moves. We have Ft1 minus friction equals m1a because now it's moving. And I'm going to solve for the tension. So it equals m1a plus friction. And now I'm going to see if I can simplify a little bit. Tension 1 is equal to m1a, but m1 is 5 kilograms. Friction is mu times the normal force. But I actually know both of those things. They gave me mu in the problem, which I'm not going to write down for space, but you have it in front of you. So 5 kilograms times A plus the coefficient of friction was 0.35. And the normal force is 50 newtons. We found that up above. So what I end up with is that Ft1 is equal to 5 kilograms times A plus 17.5 newtons when I do the math. Okay, now when I use the second thing, I'm going to deal with the pulley, and that requires sum of torques. We know that the blue forces are balanced, but we know the torques cause the rotation, and that's going to be clockwise minus counterclockwise. And that will equal the Ft2 times the radius minus Ft1 times the radius. and that will have to equal I alpha. Now I on this one, the moment of inertia for this one, it was a hollow cylindrical disc, so the I is a little bit different. It's only mr squared. So when I look at this, let's go ahead and substitute in what I have. It's mr squared. That's the mass of the pulley though, so I want to put mass of the pulley. Okay, let's see if we can get this to work. R squared. And then alpha, instead of alpha, so hopefully you're getting more accustomed to making this substitution, but alpha is A over R. So now one of the R's will cancel here, and all of the other R's will now cancel. So I'm left with Ft2 minus Ft1 equals the mass of the pulley times A. Okay, I have three unknowns, and that doesn't help me at this point. So now I do need to look at mass 2 and get the equation for mass 2. So it's Fg2 minus tension 2, which I will write correctly. And that will equal mass 2 times acceleration. So I happen to know information here, so I'm going to rearrange for Ft2. You may have to practice this if you're having trouble with the algebra. So it's going to be Fg2 minus m2a. Ft2 is equal to Fg2, which happens to be 70 newtons, minus mass 2a, which is 7 kilograms times a. Okay, the rest of this is now algebra. And I'm going to take the two equations. I'm going to take tension 2, and I'm going to take tension 1, and I'm going to substitute both of those into the torque equation so that I can get rid of all the forces and solve for the acceleration, because I need the acceleration in order to solve for the velocity. So here is what that ugliness looks like. Okay, so we're going to just start with the fact that I have Ft2 minus Ft1, this is just the equation I had from the torques, equals 2 kilograms times A. Let's make sure we have the same. Yep, all I did was put in the mass of the pulley. All right, so that's where we are. And now I'm going to substitute in all of those equations. So for T2, I'm going to put 70 newtons minus 7 kilograms times A, minus, now be careful because of the minus sign. It changes the sign in what I'm putting in for Ft1. So it's minus 5 kilograms times A plus, which will actually be a minus. So I'm going to go ahead and change it. So it'll be minus 17.5 newtons equals 2 kilograms times A. When I combine the numbers, I get 52.5 newtons minus 12 kilograms times A equals 2 kilograms times A. When I put all of the A's on the same side, I end up with 14 kilograms times A and 52.5 newtons. When I divide both sides by 14 kilograms, I get, as my acceleration, 3.75 meters in a second every second. Now, why do I have that, and what am I going to use it for? I need to have that to find the final velocity after it has fallen a certain distance. And I think the distance was 2 meters. Yes, the distance was 2 meters. So the whole thing is going to fall 2 meters, and I have to figure out what the velocity is. So here is my list of knowns. My delta y is going to be 2 meters, and I have it as positive because I've had the direction of motion positive the whole time. The initial, we're going to assume it's starting from rest. We have our acceleration from all that work we did just a second ago. And now we're trying to find V final. So we're going to use V final squared is equal to V initial squared plus 2A delta Y. And then we're going to solve for V final. I'll move it back down a little bit. So V final is equal to V initial is 0. So it's 2 times the acceleration times the delta Y, which is 2 meters. Square root of all that. I'll take the positive root when I take the answer, and it's 3.87 meters in a second. Okay, so now we're going to do the same thing, but with energy. So when I look at this problem, I'm going to think about the fact that here's what I have going on. Okay, the only energy I have to start with is the gravitational energy from mass 2. So this is 2, this is 1. And all of that energy becomes, after the distance that it falls, it becomes the kinetic energy from 1, linear, plus the kinetic energy from 2, linear, plus the rotational kinetic energy of the pulley, plus the thermal energy, because we have friction. Okay. So now I go through and I substitute everything I know. This is mass 2 times g times delta y. This is mass 1 times velocity final squared. This is mass 2 times velocity final squared. This is 1/2 I omega squared for the pulley, and this is the energy from the thermal energy that comes from the work done against friction. So to calculate that, we are going to say work by friction, and then we'll figure it out in the next step. Okay, so to substitute in, we're going to make sure we understand that I is equal to mr squared for this because it's the hollow hoop. And instead of omega, we're going to use V over R. And then for the work done by friction, that's the frictional force times the change in position that the object moves. So that's mu times the normal times that distance. But that is mu times mg, mass 1 times g, because it was equal to the weight, times the distance it moves. The delta x, this is important, the delta x is equal to the change in position of delta x for object 1 is equal to the delta y for object 2. So now when I go to substitute all of this in, I'll move it back up here, I end up with m2g delta y is equal to 1/2 m1 v final squared plus 1/2 m2 v final squared plus 1/2, instead of I, it's mr squared. And instead of omega squared, it's v squared, which is v final, over r squared. So the r squares will cancel. Plus mu m1g delta x. Okay. Now the nasty part is to substitute in all of the numbers for everything. So here I'm just going to go with 70 newtons because that was the weight, times the delta y, which was 2 meters. I'm leaving off decimals to make sure I have room. Okay, so now I'm just substituting in. So 1/2 of mass 1 would end up being 2.5 kilograms times v final squared. And 1/2 of mass 2 is 3.5 kilograms times v final squared. 1/2, this is the mass of the pulley. We want to make sure we understand that. So 1/2 the mass of the pulley ends up being 1 because the pulley was 2 kilograms. So this is just 1 times V final squared, plus the coefficient of friction is 0.35, so it's 0.35 times the m1 times g, that's the weight, the 50 newtons, and delta x is 2 meters. So now we have lots of numbers and we just have V final squared. So if I kind of break it down a little bit, over here I end up with 140 Newton meters. Then I have 7 kilograms times V final squared plus 35 Newton meters. So you can check your math along the way. And then V final would end up being when I do the math, it would be 140 Newton meters minus 35, so 105 Newton meters divided by 7 kilograms. Take the square root of that, and we'll take the positive root, and we end up with 3.87 meters in a second. So the same answer that we got doing forces and torques, but using energy. And now you can decide which way you would rather approach the problem.